Welcome to episode 14 of our series of training on robotics-inspired science education. In our previous lesson, we looked at how to implement error detection and correction using a proportional controller. In this episode, we'll be looking at error avoidance using a derivative controller. We'll implement our error avoidance program as a continuation of our error detection and correction mechanism. So in the long run, we want to have a robot that can implement implement both error detection and correction as well as error avoidance. So a quick recap. For our error detection and correction robot, we came up with an error formulation where error was our light sensor reading minus 50. Then we came up with error correction formulation or error correction formulas where motor A was moving at a default speed increased by a certain constant of proportionality we call the proportional gain multiplied by the error, and then motor D was controlled by adjusting the speed by the same proportion of the error. Now, we want to add an error avoidance principle to what we are doing. So for our error avoidance formulation, we are looking at being able to predict the error and preventing it from occurring. So instead of waiting for the light sensor to veer off the black line, so we compute how much deviation has occurred, we rather want to predict by how much it is about to deviate. Now, to make this simple, if I started writing the numbers 2, 4, 6, 8, and I ask you what will be the next number? Good. I know you answered 10. So 10. But how did I come by that number 10? Because I could track the variation of the error. So I could see that error is varying by 2. By subtracting this from that, I have 2. This from that, I have 2. So I could tell that the rate of change of error is 2. That is what we call, so the error dt. That is the rate of change of this value with respect to time. So assuming these were error values that were coming from this formula, then if we monitor the error values over time, we can come up with the rate of change of error. That is how error is changing with time. And once we know that, we can predict the next error. Now, as simple as this is, as you can tell, it is just implemented by what? By subtraction. So, if this robot is running in the loop we saw in the previous video, then for each round of the loop, there is an error value that comes out. In the first round, we have an error value. In the second round, we will have an error value. In the third round, we would have an error value. If we wanted to predict the fourth error, we could have predicted that from the previous 2 errors. So let's assume we wanted to predict the fifth. So first, second, third, fourth, fifth. Let's assume we wanted to predict the 5th error. How did we get the 10? We said the 4th error minus the 3rd error, which was what? 8 minus 6 gave us 2. And by adding that to this, we could tell that the 4th error, the 5th error is likely to be 10. So we can see that if we know the rate of change of error, then we can predict the next error. How did we get to know the rate of change of error? We used a simple subtraction, that is 4th error minus what? 3rd error. So we would say the error prediction formula, error prediction is from the rate of change, which is the current error or the error that we are measuring in our current state minus the previous error. And that gave us the rate of change, which allowed us to predict what? The next error. So this is what we need to be able to do error avoidance, because once you can predict, you can avoid. So we will say that from our previous session, we had error detection formula, and then we use that to do error correction. Now we have error prediction. We have an error prediction formula, which we'll call the derived error. Let me name it the derived error, or the predicted error, as error value minus the previous error. So once we have a derived error, this error has not yet happened. It is yet to happen. So we can use that to avoid the error from happening. So just as we had an error detection formula and we use it to do error correction, now we have error prediction or derived error, and we can use that to implement error avoidance. So our error avoidance formulation will be as simple as here. Also, they are applied to what? The motors A and the motors what? D. So motor A, to avoid the derived error from occurring, motor A will have to be moving at what? Speed plus, again, a certain constant we'll call the derivative gain multiplied by what? The error. And then motor D will also move at the speed, this time minus the same derivative gain multiplied by what? The error. So a fraction of the derived error, a fraction multiplied by the derived error. So a fraction of the derived error, which is a predicted error, is used to prevent the motors from what? Getting into that erroneous state. So there is our error avoidance formulation. What we want to do is have the robot implement both error detection and correction as we have here, and error avoidance as we have here. So there is error detection and correction, there is error avoidance. So we are putting these two formulae together, and we are going to have that as motor A is then supposed to drive at speed plus this whole thing. So Kp multiplied by the error will do the error correction, again plus Kd multiplied by the derived error will do the error avoidance bit, and then motor D will move at speed minus Kp multiplied by what? Error, doing the error correction for motor D, and then also scale it by Kd multiplied by derived error, doing the error avoidance for motor D. So what we have here is what we will call a proportional derivative controller. So the proportional controller, which we worked in the previous session, is what we have here, captured in this formula, and then the error avoidance, which is coming from the derived error, and then the error avoidance formulation is also captured by Kd by the derivative error. So as we can see, the motors at any point in time are being manipulated based on the error that has occurred, and then also being manipulated to prevent the future error from what? Occurring. So we have a robot that can now implement both error detection and correction as well as error avoidance. When we put this together, we would say we are implementing a proportional derivative controller. In the future, we'll be looking at adding an integral part, but this is what we have for error detection and correction as well as error avoidance. In our next session, we will use the EV3 milestone programming environment to implement this, and we will see how that fine-tunes the navigation of our robot. Thank you for watching. I hope you understood this video. Comment, like, and share. If you have any questions, leave them as comment and we'll address it. My name is Michael Wilson, Chief Trainer for the Ghana Robotics Academy Foundation, and also a Chief Research Technologist at the Council for Scientific and Industrial Research. Thank you for watching our video. Bye-bye.